In this video, we will discuss about the thermal stresses. Thermal is mainly related to temperature or change in environment. So, if in the engineering mechanics, if consider a body, if the body is subjected to the environmental condition, obviously either due to increase in temperature or due to decrease in temperature, there will be expansion or contraction of the body here. So the design is mainly related to, we need to consider the thermal related data also. So here some of the points are there related to thermal stresses. We'll see one by one here. Okay. The first point is, if temperature increases, the body will be expands. It means if the body is there, if temperature increases, due to increase in temperature, it undergo the deformation. It undergo deformation and it will be expands. There will be extension takes place. That is the first point. In the other words, if temperature decreases, the body will be contracts. Here the compressive load or compression of the body, it will takes place here. Okay. So no stress, third point, no stresses are developed if no constraints are applied. What do you mean by constraints here? You need to, because to avoid these stresses due to this increase or decrease in temperature in the body, in the civil structure or in anywhere in the environment, we need to apply constraints. So without constraints, there is no stresses are developed. It will expand freely if you are not apply any constraints there. Okay, that is the third point. That is, no stresses are developed. There is no stresses inside the body if no constraints are applied. That is, it expands or retracts freely. There is no any constraint due to which it will expand or retracts freely here. Okay, that is the third point. The next point is, if constraints are applied. For example, here the body is there, it will expanding due to increase in temperature delta T. If you applied a constraint, suppose it will be held rigidly between two supports. These two are called constraints. Here you are applied a rigid supports on the ends. These are the constraints to avoid the expansion. If constraints are applied, tensile or compressive stresses are developed. Obviously, to avoid the expansion, the forces, either the tensile force or compression force, it will be developed, due to which the tensile stress or compression stress, it will be developed here. Okay. The next point is the constraints. Whatever you are applying the constraints to avoid the expansion, either they may be complete or partially. I'll explain later what are the complete constraints and partial constraints here. Okay. You need to apply the different types of the constraints are there. Okay. So next point are the improper constraints. So with the not properly designed or improper constraints in the beams or in the bridges leads to buckling failure. Okay. So always remember, the temperature is one of the criteria or one of the factor. So due to increase or decrease in temperature, the beams or any body, it will undergo the deformation. Either it will undergo expansion or it will be undergo contraction. To avoid these expansion or contractions, the stresses due to which the stresses also developed. To avoid these stresses, we are applying different constraints. So that will be the design criteria. Okay. Now these are all related to the increase or decrease in temperature. We will derive the equation. What will be how the change in temperature will be affect onto the stresses here. Okay. In the first case 1, we will consider a body. That is body, and it is free expansion. This will be free expansion. Okay. So body is there and its length is L. And delta T equal to change in temperature or change in temperature. temperature or increased temperature or increased temperature. Okay, when this body is undergoes increase in temperature, obviously it will undergo the expansion. In the first point I said, if temperature increases, it will undergo extension or the deformation in tensile direction. Okay, it will undergo extension like this due to increase in temperature delta T. So the final length of this bar is, that is L plus, that is change in temperature, that is delta T due to temperature here, due to temperature. Okay, so this will be dl due to temperature here. Okay, so L is length. What is dl of T? That is change in length. It is how much change in length due to temperature. This is change in length due to delta T, due to increasing temperature here. Okay, this much is, this I can give it as change in length due to temperature. Okay, so now how much is the deformation? That is change in length. Deformation or I can write it as expansion due to delta T, due to change in temperature, equal to, this is change in length due to temperature change, is directly proportional to, just remember, always the deformation is due to change in or increase in temperature is directly proportional to its length and its change in temperature, Okay, so deformation is directly proportional to its length and directly proportional to its increase in temperature. So if I remove the proportionality constant, deformation due to change in temperature equal to alpha, this is alpha into length into delta T. Okay, this is different, this is directly proportional to, this is directly proportional, and this is where alpha is called, alpha equal to coefficient of expansion, coefficient of thermal expansion. What it means? That is, it is the strain, how much strain per unit change in temperature. Per unit change in temperature, how much will be the strain? That I can write it as, that is strain per unit degree, per unit change in temperature. Okay, so what the unit it will come? Strain, there is no unit. It will be obviously how much the strain per degree rise in temperature or per degree less in temperature here, reduced in temperature here. Okay, so what is this one? This is coefficient of thermal expansion. Coefficient of thermal expansion. So this is the main formula. The deformation due to change in temperature is equal to its coefficient of thermal expansion and length and delta T. And this coefficient of thermal expansion is, it is differ from different material. It is different for a given material. It means for different materials, its value is different here. Okay, this is the first case. It is free expansion. So when it is undergo a expansion due to change in temperature, its expansion or its deformation is directly proportional to its length and its change in temperature. If you remove the proportionality constant, I'll get the coefficient of thermal expansion into length into delta T here. So in second case, we are applying a constraints. In second case, case 2, complete constraints. Complete constraints. It means a bar, this is bar of length L. This is length L and it is held between two supports, rigid supports. These are the rigid supports. Okay, L equal to length of the bar is subjected to two rigid supports at the ends. Rigid supports at the end. So in this case, so for what purpose we are applying the supports here? To avoid the thermal expansion. Supports at the end to avoid thermal expansion. Even if you apply the supports, obviously the body due to change in temperature, delta T is change in temperature, increase in temperature. Due to this increase in temperature, the body will undergo the thermal expansion like this. Okay, so the final length is, what is the final length after expanding? It is L plus deformation due to change in temperature, that is dt of deformation, dl, deformation due to change in temperature. So this is dl due to change in temperature, Okay, now first we will write free expansion. How much free expansion due to what? Change in temperature due to delta T equal to free expansion due to change in temperature equal to, what is the formula? It is alpha, coefficient of thermal expansion, into length is the length of the bar, into change in temperature, Okay, this is the free expansion. Now to avoid this one, this is completely constrained. To avoid this one, we are applying a obviously there is the compressive load due to which compressive stress will be developed. Okay, to avoid free expansion, the compressive load or compressive stress, is developed. Okay, so it is called restrained deformation. Therefore, restrained deformation equal to, that is deformation due to restraint. This is deformation due to increase in temperature, equal to how much in terms of stresses. We know that PL by AE, in the basic formula, PL by AE, that is PL by AE, where P is the compressive load, L is the length, A is the cross sectional area of the bar, and E is the Young's modulus. So this I can write it as P by A is stress, that is compressive stress. Okay, compressive stress into length divided by E. Okay, this is the restrained deformation. Now this is 1, call it as this equation as 1 and this equation as 2 here. Now these two are same. This is the deformation due to expansion. To avoid this one, opposite, the restrained deformation will be developed. That will be equal to sigma L divided by E. Now if you equate these two from 1 and 2, we can equate alpha into length into change in temperature equal to, that is compressive stress into length divided by E here. Okay, so this length, this L cancels, therefore stress developed equal to alpha into delta T into E. Okay, so this much stress is developed in the body when it is completely constrained. It means you are completely come and it will be the stress, the compressive stress is here like this, here, and this is here. This is sigma and this is sigma. This is compressive stress. Alpha as usual, change in temperature as usual, instead of length it will be Young's modulus. That is the stress here. Now in the third case, case 3, we will write partially constrained. Case 3, it is partially constrained. What do you mean by partially constrained? Whatever you are applying the supports, that is, it will be at a clearance distance, at a clearance of certain distance here. Okay, so I'll just draw the picture, then we'll derive here. Okay, first we have body of length L. This is length L, and it is subjected to the supports. It is subjected to the rigid supports. These are the rigid supports at the left and right hand with a clearance of delta T. This distance is delta. This is delta. Okay, so from here to here, how much is the distance? This is delta by 2 and this is delta by 2. Okay, delta by 2. So total L plus delta. L plus delta here. Okay, so L equal to length of the bar, we know that length of bar, and what is the delta T? Delta T is change in temperature. Change in temperature. Change in temperature, and it supports rigidly by the clearance. The bar is supported at two ends with a clearance of how much? With a clearance of delta. So due to this change in temperature, obviously the bar will undergo the expansion. That is increase in temperature. It is increase in temperature. The bar will undergo the thermal expansion. So this from here to here, how much expansion? From here to here. What will be the distance? It is L plus change in deformation due to thermal expansion. Okay, now we know that L, we know the delta, it is clearance, distance between the two rigid supports, and after expansion the total distance is L plus dl by t here. L plus dl by t here. Okay, now the whatever the free expansion, first we will write, that is free expansion, or we will write the restraint deformation. Restraint. First we'll write the restraint deformation. Deformation equal to deformation due to restraint. Restraint equal to, we know that free expansion is alpha into T into L, right? That is alpha change in temperature into L. This is free expansion. This is free expansion. Alpha into change in temperature into L. This much is free expansion from here, from bar end to the total here, okay? Minus delta, okay? This much is restraint deformation. It means that will be comes from here to here, here to here. It is free expansion minus delta here. Next we'll get the restraint deformation, that is the compressive deformation. This will be equal to deformation due to compression, because already this much is restrained, but due to which you want a opposite the compression deformation. That is, what is the formula? PL by AE, right? AE. So if you convert, what do you mean by P by A? It is stress into L divided by E. Okay, this is the compressive deformation. So equate A and B. This is A and this is B. Both are equal. Okay, from A and B equate. That is, you need to equate alpha into delta T into L minus delta equal to stress into L divided by E here. Okay, we want stress equal to E into alpha delta T into L minus delta divided by E here, divided by L. So this will be equal to E into alpha into delta T change in temperature minus this delta divided by L. This is the stresses. So this much stress is developed in the body due to increase in temperature of delta T, and it is partially restrained, partially constrained. You are applying the supports at the distance of clearance distance of delta. Okay, this is how we need to, depending upon the situation they are given, we need to apply the conditions here. Okay.